Well, hello, friends. How we doing today? All right. So today we reach what a lot of people think is one of the harder things we do in AP calculus. That is related rates. So these are essentially nothing more than applied implicit derivatives. So we're going to walk through, we have 10 questions we're going to be doing in our notes, 5 today, 5 tomorrow. And then we'll do some problems during class as well. Got another 5 that we'll do over the next couple of days in class as well. Really just kind of get a lot of practice at this. Again, biggest thing about this is you just can't do it. You can't do too many of these. And when we're dealing with these, you're going to have to remember that when we're dealing with these, we're always going to be asking certain questions. For instance, question one is, what do we know that doesn't change? So there's always going to be some things that we know that doesn't change, that don't change. And those things we know that don't change, those are going to be useful to us because we can use those at any time we want to. If they don't change, then we're going to be able to play with them at any time. Now, the next thing we're going to have to deal with is those things that we're trying to find. And we're trying to find things at a specific time. So you can hear this phrase a lot. We're looking for little snapshots. At our little snapshot in time, what are we trying to find? What are we trying to deal with? Let's see if we can. What do we know that doesn't change? It doesn't. Yeah, we probably should have proper grammar here, right? All right. What do we know that doesn't change? And what are we trying to find at any specific time? So these are like our two big question ideas that we're going to be using over and over and over again. So what doesn't change? What are we trying to find? So as we go through here, realize that's what we're looking for. So everything we have here is going to matter. Sometimes we're going to be given values. Sometimes we're going to be giving rates or derivative values. So we need to be able to figure out, is something a derivative value or is something a rate? So let's go through and take a look here. Suppose a spherical balloon is inflated. So this right here is going to matter. We're dealing with a sphere. Now, on the AP test, they're going to give you the geometric formulas. Now, I didn't give them to you here on this because I wanted to see, first of all, what you remember from geometry. But on a test or whatnot, I would give that to you. So we're dealing with a sphere, and it says it's inflated at the rate. So now we have a rate, and realize with this rate, an important word is going to come into play here, cubic. So we'll talk about that here in a second. And it says that we're trying to find a rate. What is the rate? The radius. So we're going to try to find the rate of a radius. And that radius we're going to be dealing with is at 5 centimeters. So take a second here and ask yourself, okay, what things do we know are never changing? And what are we trying to find and what is changing? So I just realized I spelled the word doesn't wrong. Sounds about right. All right, here we go. So things that aren't changing. So sphere. I know I'm dealing with a sphere. I don't know if I'm dealing with the volume or if I'm dealing with a surface area. But this word right here is kind of a key word. I see cubic. So that means I'm going to be dealing with the volume of a sphere. So I know that the formula for the volume of a sphere never changes. So volume is 4/3 pi r cubed. That never changes. And it says it's inflating at the rate of 10 cubic centimeters per minute. In other words, I have a rate that is in cubic centimeters per minute. Well, if it's cubic centimeters per minute, and I know that volume deals with cubic centimeters, that means that this right here that they gave me, that was the rate of change of a volume. So I know that they gave me a volume. So 10 centimeters cubed per minute. So I know things that aren't changing. I know the relationship for volume doesn't change. And I know that the rate of the volume doesn't change. They asked me to find the rate of the radius. What is the rate of the radius? So I'm going to let R be my radius. So I'm trying to find radius. Now notice, every derivative I'm using here, it's not in terms of over dx like it was for implicit. It's over time, because everything is going to be done with respect to time. I was given the rate of my volume with respect to time per minute. I'm going to try to find the rate of my radius with respect to time as well. So I'm going to try to find dr dt. I'm going to try to find that, and then I have to have when. When am I trying to find that? And so that's where I'm looking for volumes that change. So think about this for a second. If I'm dealing with something that's changing, okay, so let me go ahead and draw. A lot of times it helps to have a picture to help us out with this. That being said, it's a sphere. My guess is you guys all kind of have an idea what a sphere looks like. So all right, so here's my radius. And as this sphere gets bigger, as we blow it up, the radius is changing. So imagine a balloon. When I start blowing up a balloon, it's a very small circle, very small radius. But as I blow that balloon larger and larger and larger, as it enlarges, the radius enlarges, and therefore the volume enlarges. Notice, the volume can enlarge, the rate that volume isn't enlarging. It's the same amount of air that I'm blowing into it every time. But this radius is 5 centimeters. That's the radius of my sphere. Is if it's enlarging, that's not always going to be the radius of the sphere. There's at a point in time, kind of a snapshot in time, where my radius is 5 centimeters. So in other words, there's two things I know that are not changing. I know that the equation of volume, not changing. I know that my dv dt, the derivative of my volume, isn't changing. And I'm going to try to find the rate of my radius, what the rate that is changing at that exact moment when my sphere is 5 centimeters. So the hardest part is literally just setting it up. Once you've set up the problem, then it's just a matter of just plugging and chugging. So I know I'm going to be dealing with volume here. So in order to figure out what my R is, I'm going to have to take the derivative of this with respect to time to make that dr dt pop out. So here's my dv over dt. There we go. And then I have some constants here. I'll just leave those alone. They don't do anything for me. Not yet, at least. But I do have this r cubed. Now that's something I can take the derivative of. So 3r squared. And then don't forget, I'm taking a derivative of r, but I'm going to take it with respect to time. So dr dt. So since I want to find dr dt, the next thing you always got to do on a related rate problem is get the thing you want to find by itself. So I want dr dt to be by itself. So that means I'm going to divide everything else off to the other side. So dv dt, that's going to go on top. And I'm going to divide it by everything that was on the other side. But if you notice, I can clean something up here real quick. I notice I have a 3 here and a 3 in the denominator. I can go and get rid of those. So what I'm going to divide by both sides is 4 pi r squared. So from here, now I'm able to actually find my derivative, and now I can plug everything in. So I'm going to evaluate this differential equation, and I'm going to evaluate it in now with implicit derivatives, we put x and y down here. It's only the variable at the snapshot in time we're dealing with. So since my snapshot in time is r, that's going to be the thing that I'm using as kind of that. I'm trying to figure this out when it's r. I'm going to plug that in here. So that's saying, hey, we're going to evaluate this when r is 5. That's the snapshot. So now I'm plugging in all my numbers. Well, dv dt, we've already said is 10. And then I'm going to divide it by 4 pi. And then I have my r squared. So if I plug that in there, and friends, if these are on the, again, if this is on the free response portion of the test, we are not simplifying anything. So radius, this is a centimeter, but the time we're using is per minute. So this would be centimeters per minute. Now, if you did want to simplify, I'm going to go ahead on each of these problems and give you what the simplified answer is, because I know that some of you guys are going to do it no matter what. I don't want you to, but if you do, that's okay. So if you were to simplify this, this would be 1 over 10 pi centimeters per minute. Or if you're a person that loves to use your calculator, make it approximate. Don't leave it as equals, make it approximate. And then always do out to 4 decimals. Remember, the College Board is always going to round you or grade your rounding out to 3 decimals. But if you go to 4, they don't care. Or, and you round wrong, they don't dock you. So these answers would also have worked as well. Okay. So the biggest thing we're doing on all these is we're just trying to figure out what it is we're being asked. Once you set it up, it's not too bad. I didn't mean to get rid of that. There we go. Didn't mean to get rid of that either. There we go. All right, so let's try another one, shall we? So that's our first one. Let's see what you guys can do with that. All righty. Go and pause the video. While you're doing that, I'm going to go ahead and clean off the rest of this. Pause the video and see if you guys can actually just figure out, label what it is we're trying to figure out. All right, so I have a 13-foot ladder. Notice I have a 13-foot ladder. That should say on the floor, not the floor, on the floor. And the other end rests on a vertical wall. So in other words, I'm going to have a ladder. Let me draw it, because sometimes it helps for us to be able to see it if we can actually draw it a little bit. So I'm going to have myself a wall of a building. And then I got this ladder that's just kind of hanging out there, leaning against the wall. And that ladder is 13 feet. Now this ladder is not going to change. Not told that it's an extension ladder or anything. We just know that we have a ladder that is 13 feet. Well, by the way, before I go too far here, take a look at what shape this might be. It's against a wall. That's probably a right triangle. So I think that hypotenuse of that right triangle, I believe that hypotenuse might be 13 feet. That's a number that's not changed. I'm going to throw that in there. So I have a ladder that is 13 feet long. if the bottom end is drawn away, so in other words, it's going away from the wall at 3 feet per second. So it's going away from the wall. So it was here. In other words, it's getting longer. So since that's the horizontal value, I'm going to use x because of the horizontal axis. That rate, it's going away. If it goes away and it's getting larger, that makes my rate a positive value. If it was going towards the wall where the rate was getting smaller, I would end up with a negative value. So the rate, well, that's not going to change. So that's 3 feet per second. What else do we know? What is the rate, the top of the ladder? So we're going to try to figure out the rate the top of the ladder is sliding down. So here's my ladder, it's sliding down. Again, that's a vertical axis. So I'm going to call it y. So I'm trying to figure out the rate. I'm trying to find dy dt. By the way, I already know that's going to be a negative answer when I'm all the way done because it's getting closer. It's getting, that vertical height is getting less every time. And I'm going to try to figure it out in my snapshot in time here when the bottom of the ladder is 5 feet. So when y is 5 feet, when it's 5 feet above the ground, that's what I'm going to try to figure out. Well, let's take a look at this here. I'm dealing with a right triangle. So think about it here. What do we know about right triangles? There's something else I know that doesn't change, that isn't up here yet. And if I'm dealing with a right triangle, chances are I'm probably dealing with x squared plus y squared. And by the way, I don't need to put the ladder squared. Since I know that 13 is never changing, I can go ahead and plug that 13 in here. Since I know that's this right triangle, since the ladder is a never changing value, this right triangle is always going to have a hypotenuse. That's 13. Well, now I have all my stuff. So friends, here's the equation we're dealing with here. X squared plus y squared equals 169. So why don't you guys take a second, see how far you can take this now to solve the remaining problem. All right, here we go. So we have 2x, and that's dx dt. And then we also have 2y. And on that 2y, we have dy dt. And friends, very excited. While we're in the middle of the video, one of my favorite people at this entire school is here. So everybody's favorite head custodian, Rick, is here. Rick, how you doing? Good, man. All right, and then the derivative of our constant number, the derivative of 169. Well, any constant number, by now you guys know that's always my favorite. It's 0. But now let's stop for a second, because if we're looking at this, friends, we have dx dt. Well, I know what that is. I'm going to plug that in, actually. I know my dx dt is 3. I know my snapshot in time, and I'm going to erase this step because my notation isn't right here. I'm going to erase it just so you guys can see it here. I know my y value is going to be 5. And I'm trying to find dy dt. And friends, if you're awake and I haven't put you to sleep yet, you're going to notice something. There's something we don't know. And friends, that's pretty much how it is in a lot of things. A lot of times in life, we don't know that we don't know something until we don't know it. We didn't know that we needed to know the value of x in order to do this related rate. We didn't know that. As we get to the problem, we come back and we realize, oh, that's something that we needed to know. You know, a lot of times, if there's something you don't know in life, as it pops up, no reason to freak out, no reason to panic. Just go figure out what it is you don't know. So I'm going to go back to my original related rate, or my original equation here. And I know that when y was 5, that was a snapshot. But when y was 5, that means x had to also be equal to something. So a lot of times on these related rates, you're going to get in the middle of the problem and realize, oh, I need to stop for a second because there's something I don't know. In this case, I didn't realize that I needed to know the value of x. That's okay. Don't need to lose sleep over it. We're just going to stop for a second. And like I told you before, I'm going to go back and erase that equation where I was plugging stuff in because my form is not good on that. And we don't deal with negative radicals here in geometry, so that means I'm going to have a 12. So when x is 5, it turns out, when y is 5, turns out that's when x is 12. So I'm actually trying to find dy dt when y is 5 and x is 12. I have two things that are changing that are going to help me figure out this value. So we come back here. And now I can go ahead, and by the way, I do notice something here, friends. I hope you guys notice too. I have 2 on everything. If I divide out everything by 2, I'm going to be left with x dx dt. If I don't do it now, I'm going to have to do it later. If you're a person that simplifies. If you're a person that doesn't simplify, you don't care that those 2's are there at all. And again, you do not ever have to simplify on the free response portion of a test. So we're trying to find dy dt. So I'm going to get dy dt by itself. So that means I'm going to move the negative x dx dt over. So negative x, I'm subtracting that to the other side. And I'm going to divide the whole thing by y. So now we're ready to go ahead and evaluate a little bit. And one of the things you guys are going to find out over and over again, these related rates, some of you are going to find them extremely hard. Some of you guys are really going to like them, which I think is cool. I think they're fun, but then again, I'm a calculus teacher. But you're going to notice that there's kind of a pattern. There's kind of a flow to them. They always kind of ask the same questions. I don't know why I put an R there. So when y is 5 and x is 12, I can go through and figure out what dx dt is. I meant dy dt. All right, so we plug everything in there. So I have a negative x is 12. That was a very ugly 2, wasn't it? There we go. So I have my 12 in there. And my dx dt, well, dx dt we said at the beginning was 3. And y, well, that was, what was y? That was 5, wasn't it? Notice how we said the ladder is getting lower. The length of the ladder, the height of the ladder is getting lower. And if it's getting less, therefore it should be a negative rate. Well, if you notice, there's our negative. It's going to be a negative rate. So then that would end up being feet per second. And again, I wouldn't do any sort of simplifying. I know some of you guys will. Some of you will simplify. And hey, if you do, you do. I mean, I'm not going to lose any sleep over it. All right, if you do, that's fine. So for my friends that simplified, that might be negative 36 over 5 feet per second. Or if you're a person that likes decimals, totally good with that as well. That's negative 7.2 feet per second. I am struggling writing 2's today, man. Using the mouse as a pen when we have those curves, those are a little bit tougher. So So either of those would be fine. Again, I wouldn't simplify, I would just leave it alone. All righty, friends. I think it's time for us to try another one here. And again, this is just going to be kind of just drill and kill. You just got to practice these. I mean, I know some of you are like, oh, man. No, it's fine. There you go. All right, why don't you guys pause the video and see, again, just try to set it up, and then we'll talk about it. Just try to set it up, and then we'll talk about it. All righty, here we go. Let's see. Water's poured into a conical cup. Conical. Root word for conical is cone. So we have a cone. All right, see if I can make a cone here. All right, that kind of looks like a cone a little bit, right? Become a math teacher, you have to become a professional shape drawer. And I'm going to have a conical cone. A cone is represented always by some R value and some H value. That's always a right triangle. All right, so what do we know here? We are told that the rate of the cone is flowing in at cubic inch. Oh, there's that key word again. Did you see that? Cubic. That tells me I'm going to go back to my cone here. The particular thing I'm dealing with my cone is volume of a cone. And if you don't remember what the volume of a cone is, don't worry about it. The College Board will most likely give you that one. Again, I just wanted to see if you remembered or not. 1/3 pi r squared h. I forgot the pi. Friends, don't ever forget the pi. I could go for a peach pie right about now. I tell you what. Mrs. Williams made me a peach pie for my birthday. Oh, so good. 1/3 pi r squared h. All right. So I know a rate then, and the rate I know is a cubic rate. So therefore, I know the rate of the volume. Rates don't change. The rate they gave me will not change. So my volume is getting poured in at a constant rate. So my volume is increasing because the water is getting poured in. It's not getting poured out. It's getting poured in. At 2/3 inches cubed per second. So the time I'm going to be taking every derivative to is with respect to is seconds. If the cup is 6 inches tall, oh, there we go. If the cup is 6 inches tall, well, which of these would be tall? How tall it is? The radius or the height? Yeah, that's going to be the height. So the cup is 6 inches tall. I'm going to put that up here. I know the height of that is 6 inches. And the top of the cup has a radius of 2. All right, so these are just the dimensions of the cup. It said, what is the rate the water level is rising? So what's the rate the water level is rising? Well, rising, is that H or is that R? Right, it's H. So I'm going to try to figure out dH dt. When what? I'm going to try to figure it out when the height, when that height is 4. So there's going to come a time when this water is going up, and it's going to stop here at 4. It's going to have a height of 4 inches. Well, so I'm going to, now, I'll be honest. I'm trying to find the rate of the height when the height is 4 inches. So I guess I'm kind of looking at this thing wondering, what about the radius? And so this is where we kind of stand with the radius. If we notice, my original volume equation had two variables, R and H. I really want to only deal with one. So no matter what, as the water's going up, can you see how it forms like this orange cone? As the water is rising, there's always a cone inside the purple cone, an orange cone inside the purple cone. So as the water is rising, I'm going to have to deal with the rate that my height and radius will relate to each other. So quick little timeout here. I want you to see something. Oh, purple. A cone is made up of a right triangle. You can see the right triangle in there, and then it spins like 360 degrees to make the cone. Well, the size of this cone is 2 inches for the radius and 6 inches for the height. However, as the water goes up, there's other cones that are formed that have a new radius and a new height. The one that we're trying to deal with is when the height would be 4 inches. But there's an infinite number of cones. So as water gets poured into the cone, and that water level slowly starts to rise up, it's creating cones out of the water inside our cone container. And there's something I remember back in geometry, is that these right triangles tend to be similar because they both have the same congruent angle here, and they both have the same right angle. These are similar triangles. Well, there's a way that I can get rid of that R and write my volume in terms of just one variable. So for instance, my big triangle radius over its height is going to be any triangle inside of it, its radius over its height. And if I simplify that, I find out that 2h, a little bit of cross multiplying here, equals 6r. Some of you are going, wait a minute, I don't see where that 2 and the 6 and the r and the h are coming from. That's okay. Let's see if we can find it. Look at the purple triangle here. The radius was 2. The height was 6. Look at the orange triangle there. The radius was r. Oops, I drew it over the arrow. The radius was r, and the height was h. Cross multiply, you get your 2h equals 6r. So now, if I wanted to get rid of the height and put everything in terms of the radius, I could do that. I could divide both sides by 2 and get the height by itself. That's not what I'm trying to get rid of here. I'm trying to get rid of the r. I don't want to deal with the radius anymore. So instead, I'm going to divide both sides by 6. And friends, when we do that, we find out that there's this relationship that's always going to exist. It's a constant relationship. For this particular sphere, or cone, the radius is always 1/3 the height. So here's what we can do with that. We're going to come back over here. I see my volume here, but I have a way to get rid of that radius. In place of r, I'm going to plug in 1/3 the height. So if I were to keep going here, then I have the volume is 1/3 pi times 1/9 h squared times the height, or the volume of this particular shape is 1/27 pi times h cubed. Now notice, my r is gone. Now that's a tough one, friends. I don't want to pretend that one's easy. That's a tough one. But good news, now we know what equation we're going to be dealing with. So, like I said, the biggest thing a lot of times is just figuring out how to manipulate the problem to get it set up where we can solve it. Because if I give you the piece of information and the actual ending equation, you'd be fine. Well, why don't you guys go ahead and pause it and see if you can actually come up with the dH/dt. All right, here we go. So I'm going to take my derivative of my v. dv dt is 1/27 pi. So leave those constants alone. Times 3h squared dH/dt. So this part always stays the same. I'm going to do a little quick canceling here. The 3 will go into the 27 9 times. So when I'm trying to get dH/dt by itself, I have dv dt and I'm going to divide it by 1/9 pi h squared. I'm telling you, I am struggling making 2's here with the mouse. So 1/9 pi h squared. Now we can plug and chug. So dH/dt, draw that all the way down there. We're dealing this when h is 4. All right. That's our snapshot. So we plug in our values here. Let's see your dv dt. I had that at 2/3. Sweet. And the whole thing is going to be over 1/9 pi. And then I have my h squared, which would have been 4. And friends, again, I can't say this enough. I would not simplify this on the FRQ portion of the test. Leave it alone. Leave it alone. So, but like we said before, I know some of you guys will do this. So if you want to know what the actual answer is, it's 3/8 pi inches per second. Or approximately 0.1194 inches per second. All right. Again, friends, that's probably the hardest one you'll see right there, that cone. Okay. We'll try some, and we're going to be doing some more cones as we go through these. Let's try another one here. See what you guys can do with this one here. All right, go ahead and pause the video, and then we'll take a gander at it. All right, friends, here we go. I am walking towards a street light. All righty. You know, that's what I've always lived for. And because I'm walking towards a street light, I'd like to draw a picture of that. So here's my street light right here. That was an ugly street light, friends. Ugly street light. Let's try that again. I can make a better street light. Whoop, there it is. There's my street light. Let's put a little light at the end of that. All right, I got a little street light there. Beautiful. And I'm walking along the ground. It says it's flat ground. That's kind of nice. So I'm walking at the rate of 5 feet per second towards a street light. So I'm just going to use a line for myself here, friends. I'm going to use green for my Oregon Ducks. Go Ducks. All right. So if I'm going towards a street light, that means I'm dealing with this value from here to here, and it's getting shorter. Okay, so just for the time being, let's go ahead and call that x. So that's a horizontal distance, and it's getting shorter. So realize, again, if it's getting shorter, that means my rate is not just a normal rate. My rate is a negative value. So dx dt, it's not just 5 feet per second. It's going to be negative 5 feet per second because my distance to the street light is getting shorter. All right. Now, it says the lamp is 20 feet above ground. Well, friends, this is something that is never going to change. This value right here, never going to change. All right, so I'm just going to leave that there. So the height of this lamp is 20 feet, not changing ever. Ever. And it says, if Mr. Williams is 6 feet tall, all right, I'm not really 6 feet tall, but for the point of this, let's assume I am 6 feet tall. Again, not changing. So we'll just say, Mr. Williams, not changing. I am 6 feet tall. So these values right here, lamp is 20 feet. Mr. Williams is 6 feet. Determine the rate of change of my shadow. Oh. Well, let's think about what makes a shadow show up. The shadow shows up when the light comes down and hits the ground. So the shadow is this value right here. I already used x, so let's use a different value. Let's call it, doesn't matter. We can go ahead and call this y if you want to. We can call it something else. It doesn't matter. I'll just stick with y here. So there's y. So they want me to figure out the rate my shadow is changing. So dy dt. And try to find dy dt. When I'm 24 feet from the base of the lamppost. So when x is 24. Okay, well, let's see what we can do with this. Friends, I don't know about you, but I actually see a couple triangles again. And I need to kind of play this a little bit here because right now, friends, I don't have an equation that I'm taking the derivative of. That's a slight problem. Kind of need to have an equation. So we said the height of the lamppost was 20 feet. And the length of the big triangle is x plus y. Y did not really show up real well, did it? That's all right. And then Mr. Williams here, my smaller triangle, 6 and y. And again, it looks like we are dealing with special right triangle. So I might be able to figure out an equation that would work. So 6 over 20, those are corresponding sides. So I'm going to use my similar triangles here, is y over x plus y. And I'm going to play with this a little bit. I'm going to cross multiply these here. So let's see here. If I cross multiply them, I'd get 20y equals 6x plus 6y. So then if I bring that over, I'm going to be left with 14y equals 6x. Well, friends, now I have an equation. 14x, and that's something that's not going to change. 14y equals 6x. I have an equation. All right, go and pause the video and see if you can finish this all the way out. All right, here we go. So I take the derivative of this side, 14 dy dx, or I'm sorry, dy dt, equals 6 dx dt. Look at this. I'm supposed to do this when x is 24. Friends, I didn't need to, I don't really need to know this for any value. That's okay though. So dy dt equals 6 dx dt over 14. So plug in our values. Dy dt. And we are evaluating this, even though we don't use x equals 24, I'm still gonna put that down here. X equals 24, well, that's not quite the shade of blue I wanted. That'll work though. And this equals 6. Let's see what dx dt was. That was -5. All right. And that would be over 14 feet per second. And again, don't simplify. On the free response, do not simplify. But because I know some of you guys just can't help yourselves, you end up with, oh, what would I get here? Oh, is that -30 over 14? So -30 over 14 would be -15 over 7 feet per second. Or, I'm not sure what that value is, actually, to tell you the truth. Just realized I never figured that one out. Or that's going to be approximately -2.1429 feet per second. All right. All right, all right. Well, friends, go ahead and pause the video one more time and see if you guys could, oopsies, undo. Do it one more time. Why don't you guys scroll down to number 5. I'll be there shortly. See if you guys can try it one more time. And then we'll call it a day. Like I said, we're only doing the first 5 today. We'll do the next 5 tomorrow. All right, go for it. All right, here we go. Let's see what we know. Circumference of a circle. All right, I know what circumference is. 2 pi r. I can do that. But it tells me the circumference is expanding at a rate of 8 pi inches per second. All right. dc dt, that is 8 pi inches per second. Determine the rate of the area. Wait a minute. We haven't even talked about it. I thought we were talking about circumference. All right, well, it looks like we're doing dA dt. And by the way, if I'm doing dA dt, that means there's something else that I know here. I better go ahead and bring in my area formula. All right, when this circle has an area of 125 pi square inches. Okay, so when area equals 121 pi square inches. I don't have to draw a picture on this one. I'm pretty sure we all know what a circle is, but just in case, friends, this is a circle. Ooh. All right, well, what thing am I playing with here today? I'm playing with area. Pi r squared, here we go, area. That's gonna make my dA dt pop up. There it is, looking proud. Equals pi times 2r times dr dt. Now, friends, I don't know about you, but I have a big problem right now. I don't know anything about r, and I don't know anything about dr dt. I don't see that out here, and I don't see this out here. But maybe we can use things we know. For instance, they did tell me that I'm doing a snapshot when the area is 121 pi. Well, if the area is 121 pi, I could probably go back and figure out what that r value is that gives me that. So, oops, forgot my pi. That's twice now I forgot pi. Mrs. Williams would not be happy. 121 equals r squared. Take the square root of both sides, and I get 11 equals r. So I'm trying to actually find dA dt when the area is 121 pi inches cubed, or and for that matter, and r is 11 inches. Well, it still doesn't help me out with dr dt. There's got to be another way that I can figure out where dr dt is, and that's where I'm looking at it here going, I was given another equation. Maybe I should play with that for a second. What if I were to play with that? I would get, so I know that circumference is 2 pi r. And if you notice, I was also told, given the derivative of the circumference. So maybe if I play with that equation just for a second, I could possibly get the piece of information that I want. Again, we don't always know what we don't know until we find out, friends. We don't know. Well, there's my dr dt. And notice it's constant. So that means dr dt, that's equal to dc dt over 2 pi. How about we solve this one real quick to figure out what dr dt actually is? So this happened when because my circumference, the rate of my circumference is 8 pi. So today is kind of our introductory look. Gets us thinking a little bit. And some of you are going, I'm not very happy right now. It's okay. It's okay. We're going to be playing with this a little bit. We're opening up our minds. Notice how we're doing pretty much the same thing over and over and over again to figure this out. So it turns out dr dt, well, that's actually equal to 4. Turned out I actually knew another rate. That rate's not ever going to change either. Turned out I knew the rate, the radius was expanding. It was 4 inches per second. So friends, now we can come back and take a look at this area equation one more time. The derivative of my area, I'm going to evaluate this, not when the area is 121 pi inches cubed, although it is. I'm going to evaluate it when r is 11. Because when r is 11, I can plug all these fine handy dandy numbers in there. Times my radius is 11. And I'm going to multiply that by my dr dt. My dr dt, that was 4. We just had to do a little bit of work to figure out everything we needed. And since this is area, this will be inches squared per second. Seriously, my twos have, I've been really struggling right at my twos today, haven't I, friends? And for those that want to know what that simplified value is, we can come up with that here. That will be 88 pi. Again, I would not do this. I wouldn't have gone any further. Although for the third time today, I forgot pi. .88 pi inches squared per second. Or if you want to use a decimal, you can. 276.4602. Inches squared per second. Notice how each of these answers had that unit of measure after it. If we're given unit of measures, we have to make sure our answers have unit of measures. All right, friends, that's a lot. It's gonna be quite a bit tomorrow as well as we continue diving through this. So keep working. You're gonna get there. Just keep working.